So thanks very much. Thanks very much for including this paper. This is work with Joao Guerreiro and Sérgio Rebelo. Joao is here. And it's about taxing robots. So a rise in automation is possibly going to increase income inequality by replacing workers in routine tasks. I mean, there's some evidence, it's somewhat mixed, but the concern is very clear. Now, we have nothing to contribute to the empirical part. This exercise is a theoretical exercise, a quantitative exercise, but a policy exercise. So we are asking whether we should tax robots. So the first thing we do is we take, we are now extending this. We take a simple model, a static model. We're going to have routine and non-routine workers, and robots are intermediate inputs in production. It's a very standard setup. And we do optimal policy exercises. We do Milesian optimal taxation and Ramsey optimal taxation. So the difference is whether you have informational constraints or direct constraints on instruments. Okay, briefly, through the model. So we have two types of agents, routine R and non-routine N, with preferences of a consumption, labor, and G. Consumption is income minus a tax function, and it's important that this tax function is non-agent specific. So it's the same tax function for both agents. You cannot really discriminate on these tax functions. Now there's a final goods producer. The final goods producer uses non-routine labor, and then for a continuum of tasks, uses either routine labor or robots. The tasks are not perfect substitutes. There's some elasticity, but the use of robots or routine labor is as perfect substitutes. So M is the level of automation, is the share of tasks that have been automated, and the model is linear in this choice. Okay, the cost of producing a robot is independent of the task, it's some fee. And this is the profit of the final goods producers. I mean, the important thing to notice here is that there is a linear flat tax on the use of robots. This is the cost of a robot. This is the total use of robots. Okay, so again, the model is very simple. If there's automation, we are going to have the same wage for the routine worker as the cost of a robot, gross of taxes. And the wage of the non-routine is also going to be a function of exogenous parameters and the tax rate, the tax on robots. So if you decrease the cost of automation, if you decrease this fee, you get that the wage of the routine is going down and the wage of the non-routine is going up, but you can reverse, you can compensate this with an increase in the tax. Okay, so the first thing we do is we take the now very standard tax function of East Coast storage Latin and Violante, estimated to US data. We take it to this simple model. So that's a function that has two parameters, progressivity, estimated to be around 0.2, and some level of taxation, which we adjust to balance the budget. We set the robot tax to 0, G to 20% of GDP, and for simplicity, we take a log function. And this is what we get. So this would be the status quo. This is what would happen if we get the cost of producing robots to go from some symmetric number of 0.5 here, that would, for our choice of parameters, would have these two agents be on equal terms with the same wage. If we lower the cost of producing robots to 0, what would happen in this economy? So we get the wage rate of the routine to go to 0 and the wage rate of the non-routine to go up. And we have these two agents work the same thing. I mean, that's a feature of preferences, of log preferences. So the routine are getting a 0 wage, working the same thing. Their income is going to 0. Their consumption is going to 0. They are not benefiting from automation. The only beneficiaries from automation are the non-routine. So this is the pessimistic world where robots are displacing routine labor and they are impoverishing them. And you'd get it with the status quo tax function for the US. Now what would be an optimal redistribution scheme if there were no information constraints? I mean, the optimal thing is trivial here. If these two agents could write an ex-ante contract, they would have the same consumption, the more productive would work more. But this also means, and actually would work more, and the routine labor would actually stop working and leave off transfers. That would mean that everyone would want to be routine. That also means that if you cannot identify the types, you cannot implement this scheme. So that's the reason why we look at constraints, informational or exhaustion constraints on instruments. Okay, so when we do Merlees, we assume that types are not observable. We assume that the labor supply is not observable. Only total income is observable. We still assume that the tax rate on robots is a flat tax. And we solve this problem where we maximize the weighted average of utilities subject to a resource constraint where the robot tax is introducing a distortion in production, a production inefficiency. And we have the incentive constraint of the non-routine be binding. The non-routine would want, in the first best, would want to be routine, and we have to prevent them from doing that. So the idea here is that we have to prevent the non-routine to prefer to have the income of the routine working the hours according to their productivity. Now, with this, we get that it's optimal to distort production. It's optimal to have inefficiencies in production. And the reason is that in this model, you have this information constraint that you are able to relax by using this robot tax. So the robot tax is going to raise the productivity of the routine and lower the productivity of non-routine, increasing the number of hours that a non-routine would have to work in order to pretend to be routine. So by using the robot tax, we relax the information constraint. This is first order. Production inefficiency is second order, and we want to have it. So this is Merleesian taxation. So we still have the wage of the routine going down, the pre-tax wage of the routine going down, and the wage of the non-routine going up. But now we have the routine agent reduce the number of hours, eventually stopping working, leaving off transfers. In the Merleesian setup, you have transfers. They are not agent-specific, but they are there. And look here that we want to tax robots. We don't want to tax them much. The rate goes up to 10%. Eventually becomes 0. It's going to be very fast. Okay, there's an alternative scheme. It's 30 seconds. Okay, there's an alternative scheme. It has a lump sum transfer. So we can, instead of doing Merlees, we can improve the tax function we saw before, the status quo function, using adjusting for progressivity, but also giving a lump sum to every agent. So it's like a universal basic income. If we do that, we get very close to the Merleesian setup. But now we get robot taxes to be all the way up to 40%. So they are sizable. Now, we do endogenous occupation. I mean, the bottom line here is that we are taxing intermediate goods. And we should know better. We should know that taxing intermediate goods is not optimal. Production efficiencies are not optimal. So why are they optimal here, the inefficiency? I mean, the reason is that, I mean, in the classic result of Diamond and Marlies allows for taxation of all net rates. But in this setup, the labor of the two agents is different net rates. But that's discrimination. I mean, we don't allow for that in the model, and most likely we could not get it in the world. I mean, the other result is a result with information constraints. We also know that in models with the information constraints, it's not optimal to have production inefficiencies. But the reason is that, I mean, those are very simple setups where productivities are exogenous. In this model, you can adjust these productivities. You can change the robot tax in order to affect these relative productivities. And by doing that, you have general equilibrium effects, and you are able to improve upon the allocation. The reference is 92. Okay? Thank you.